Hey everyone, welcome to Linker D-Day. Good to see everyone here. So as Flynn said, I'm going to be talking about the negatives to a per host service mesh, the Sidecar model being a more ideal solution, the Linker D way, and providing a more robust security boundary, so focusing on security. So my name is Chad Crowell. I am a DevSecOps engineer at Raft, and I'm also the author of the book called Acing the Certified Kubernetes Administrator Exam. I'm a CNCF ambassador and also a SIG contributor. So at Raft, we work with federal and public agencies in the US to scale cloud-native ecosystems with a security-first approach. So this is a topic of interest for us. So let's go through the objectives, what we'll talk about in this session. We'll first talk about the Sidecar versus the per-host debate, how it came about. Then we'll talk about Sidecar proxies and how they work in both scenarios, both at the pod level and at the host level. Then we'll talk about the security implications of a per-host model. And then we'll wrap it up with a summary of how to move forward with improving the service mesh overall. So why have we been talking about getting rid of the Sidecar proxy? Seems to be a pretty big debate. You've probably heard of it. What's the big deal? Well, in certain service mesh proxies, Envoy, the overhead impact of sidecars can be severe. So there are some resource requirements of the proxy, the ability to scale the proxies up and down really fast. Sometimes there's issues with jobs and apps that start before the sidecar, so like init containers, for example. Sidecars also require converting every TCP connection into a three-way segment, so the three-way handshake. So also, when you're doing TLS handshakes, additional or multiple TLS handshakes introduce additional latency as the repeated communication back and forth happens. So sometimes that takes more than up to 2 milliseconds or more to encode and re-encode L7. And proxies, they don't support non-TCP and multicast transports. That could be an argument. So UDP, ICMP, and other protocols carried by IP. So these are some of the problems that sidecar proxies, or probably why this debate is so popular now. These are some of the problems that have been presented. eBPF has been a proposed solution to this. So eBPF, I'm sure you've heard of it, is a in-kernel sandbox virtual machine. So instead of writing a kernel loadable module, we can write a set of instructions in user space and send it to the kernel, have it do stuff in the kernel directly. For example, let's say you want your application to process network packets. You can give the app a set of instructions that execute at the kernel level. Now it can get access to the machine's network buffer directly and skip the passing back and forth between user space and kernel space, or kernel space. So now that we have eBPF, many have announced to the world we can now go sidecarless. But this is a big but. eBPF is just not able to take the place of proxies, and here's why. So eBPF is invoked at the kernel at a certain hook point, so it doesn't just arbitrarily execute code. eBPF programs are not Turing complete, and for good reason. So for the safety of the kernel, it operates this way. Also, eBPF programs have to be verified to terminate. The kernel has to know that the eBPF program will terminate at a specific time. In addition, all eBPF programs must pass through a verifier. So if the verifier rejects the program, the kernel won't run it. So naturally, this verifier has to err on the side of being restrictive. After all, we are talking about the kernel. So eBPF programs can't just start and execute logic, right? Like I said, they're Turing incomplete, so they have to execute in a finite time. So as a result, eBPF programs are very limited. For example, they cannot block, they cannot have unbound loops, they cannot exceed a predefined size. They're also limited in their complexity. The verifier evaluates all the possible execution paths And if it can't complete within some time limit, or if it can't prove that every loop has an exit condition, the program doesn't pass. So now that we know that we can't just simply apply eBPF and have sidecars disappear, let's talk about the proxy being at the sidecar versus per host. So because of the problems with sidecars that we just discussed about resource requirements, latency, support for other protocols, etc., some have devised a solution to move the proxy to the host instead of being at the pod level. And as you may have guessed, this is the crux of my talk today. So let's talk about some of the problems that I've discovered when moving the proxy from the pod level to the node level. So the first problem we have, or first problem that we run into, is overhead. Even though you just have one proxy at the node level instead of having a proxy for each pod, you have a lot of overhead issues. So this comes in the form of an application consuming a high amount of resources on the host, which in turn allows the sidecar to also consume a high amount of resources on the host. This impacts other applications running on that node, and this presents a noisy neighbor problem. Another issue that we run into is resource management. So when you have a proxy per host, a single host is now managing traffic for a seemingly random set of pods. The proxy is completely decoupled from the application, so app failure is hard to track, and the implications of performing maintenance tasks becomes a little bit less predictable. You also widen the failure domain. So when you have a proxy at the host level, the blast radius increases, right? So if a proxy fails, there's a greater impact on all the other apps running on that same node. So if there's a proxy malfunction because that proxy is servicing many applications all at once, there's a single point of failure there. And then most importantly, there's the security aspect of it. So when you have a single proxy per host, performing MTLS becomes far more complex and leaves you vulnerable to the confused deputy problem, if you've ever heard of that. So the confused deputy problem means that the proxy is vulnerable to being tricked into misusing its authority. As a result, any CVE in the proxy introduces a vulnerability to the entire host. And because it's at the entire host level, that vulnerability allows bad actors to possibly impersonate every network on the node, or every network node, I should say. So moving on to the alternative, or the Linkerd way, we have with sidecar proxies, we have a more clear security boundary, right? So the security boundary is at the pod level, so it's a very smaller boundary. The sidecar is within the same security context as the application. Therefore, it gets the same IP address, it enforces the same policy, it applies MTLS to traffic to and from the same pod, and it only needs the key material for that pod. Also, another good thing is that it mirrors the app consumption. So the resource consumption scales with the load of the application. This is a good thing because as we talked about in the last slide, we don't have that noisy neighbor problem. But not only that, if the application is consuming very little traffic, the proxy also doesn't need to consume a lot of resources. And then another benefit of the sidecar model is the ease of maintenance, right? So maintenance to the proxy is handled in the same fashion as maintenance to the app, whether it's rolling updates or blue-green or canary or what have you. So now that we know the downside of a per host proxy and some of the benefits of a sidecar proxy, how do we move forward, and how do we kind of take that and improve the after all, it's an enterprise grade, right? So how do we improve the service mesh overall? And kind of my argument is making the sidecar model better, as opposed to trying to get rid of it entirely or move it to to a per host model. So since we've discovered that eBPF will never be a replacement for the L7 proxy, let's let the proxies do what they do best at layer 7, and let's let the lower level protocols do what they do best at L3 and L4, instead of trying to combine L3, L4, and L7. For example, when the Sidecar proxy is deployed to a pod, instead of using an IP tables redirect, we can use sock map in eBPF to talk directly to the proxy from within the pod. So instead of traveling through the TCP stack multiple times, which could provide that latency, it would utilize socket maps to intercept the traffic to the application, send the traffic to the proxy directly, accelerating communication and eliminating those trips back and forth through the TCP stack. Another way we can think about using eBPF to improve the service mesh is when it comes to observability, right? Because we can only observe the metrics that are part of the service mesh, we can't see other possibly critical issues within our environment. So things like issues at the Linux kernel level, for example. And that's where eBPF shines, really. In this case, we could use eBPF to observe applications, whether they're a part of the mesh or not. So everything in our environment, which is nice. For example, in a previous talk by Brendan Gregg at Netflix, he was using biosnoop, where he finds a log rotation service, which is causing spikes in disk utilization, which is not necessarily something that service mesh would catch. So looking ahead, eBPF has a long way to go before it can replace the Sidecar proxy, and maybe that's not even where we need to be focusing our efforts, right? Maybe that's a lost cause. We've definitely realized that a per host model introduces a whole host of other issues and making my job as a sysadmin more challenging. And then overall, let's start to focus on augmenting the service mesh, focus on improving the CNI with eBPF at layer 3 and 4, and let's keep on focusing on improving the proxy at layer 7. So improving the Sidecar model, as I spoke to before. And that's it. Thank you all for listening.
Thank you. We actually have, I already see questions. Yep, we have a few minutes for questions. Hang on a moment.
Please.
Hi. I guess is this talk more like proposal, not based on like, I was wondering, is there any actual in production user stories of an eBPF host model failing? I guess that's the first part, like, or is this more like proposals of how to make it better? And then what would you say is some good examples of like using Linkerd in the Sidecar? What can we use for CNI eBPF? Like, would you recommend like Cilium or a Calico kind of thing, using that together?
Yeah, so to answer your first question, actually Linkerd 1 used a per host model, and actually William had a good article on that, talking about the history of Linkerd 1 and how some of the user stories that you're looking for will be in there. So look that up. And to answer your second question, yeah, we can use tools like Cilium, and that's probably the best use case for improving the CNI.
Anyone else? One moment.
So I'm not really familiar with, but I've heard of the ambient mesh, which I think is in the Istio space. How's
Right.
this related to that?
Yeah, so ambient is a daemon set, which is essentially a per host model as well. And so I think I've heard that ambient has some efficiencies when used with GKE specifically, in terms of kind of kind of merging together the L3, L4, and L7, as we talked about before. But I think there still comes the complexities, especially outside of GKE, when you're trying to merge all those things together. It's not a silver bullet. You still start to recognize some of the downsides that we talked about, and start to run into some of those same problems. So even though, ambient is a daemon set, technically a per host model, I think you still have those problems, especially outside of GKE. So. Anybody else?
Hey, this is William. I can add a little color to the first bit about the per host proxies, kind of failure mode in practice. Like Chad said, if you go, the original version of Linkerd, the 1.x branch was all per host, and Monzo was one of the big early adopters. And if you go back in time and read some of their early blog posts about some of the struggles with Linkerd, you'll find some of the, I think that's probably the clearest kind of production story we have around the challenges they had. A lot of those were operational challenges, I think, more than security challenges. The security one is more of like a theoretical one, like, okay, per host model, we're mixing all of our TLS certificates, into the memory of one process. Do we have an actual story of someone breaking in and like stealing those certificates? No, not that anyone has talked about, but the operational ones are in some of those Monzo blog posts. It's things like, if a proxy fails, or if we're trying to upgrade an individual proxy, then all the pods on that host, are affected, and those pods are not. They're like a random set of pods from random applications, right? So whatever Kubernetes decided to schedule on that node, so it's not even correlated with, we're going to do maintenance on this service or whatever. It's you get a random cross section that gets affected by either failure or upgrade. So yeah, check out the early Monzo blog posts, I think, for some examples of per host. Obviously, it was not with eBPF. It's like eBPF was still I think a dream back then, or certainly hadn't made its way to Kubernetes. But the fundamentals are the same.
Yeah, you can also find me on Linkerd Slack, and I can share with you all of the research that I did for this talk. And I'd love to talk to you.
Anyone else? Questions? All right. Well, in that case, thank you, sir.
Thank you.
We have by all means.